Yes, so I hope everyone sees my screen.
Yes, Marcel.
Good. Then, yeah, today, I mean, just to recap, until now we have been talking about synchrotrons, mostly, like in the very first lecture, we had a brief recap on laser physics and also other um, X-ray radiation sources, but then it was mainly on synchrotrons, which are basically the basis of X-ray free electron lasers, as we will see today. And so last uh, weeks and yesterday, basically we followed the path of the electrons from their birth in the electron gun through the different acceleration stages, storage ring, undulator, to produce undulator radiation, and then we followed the uh, photons along the beam line up to the target. And of course, there's many more things to talk about when photons hit the target. How do we detect them? What kind of experiments can we do with the photons? And this could be one or two more lectures in January to give you some glimpse of all the different types of experiments that can be done at synchrotrons, where there's, of course, a very wide variety and very interesting ones. So we could possibly find another time slot in January, but and just as like a very start, yesterday we gave you I started talking about diffraction of X-ray, which is really the most important application of synchrotron radiation, like diffraction of X-rays on crystals, but also non-crystalline samples in order to get structure information. In particular, for biological systems like proteins, this is an enormous field of research. And that also actually motivated the development of free electron lasers. And like what new types of experiments we then can do with free electron lasers that cannot be done with synchrotron radiation. This will be one of the goals to get to uh, once we are done with the discussion of how FELs work. But today, so then we want to see how FELs actually work before then getting to applications of FEL radiation to do specific experiments, which we will hopefully also, or we will talk about that in January, also in the frame of this journal club, where I hope all the people who have chosen um, publications to read and then to talk about have already started doing so, so that then in January we can have these short presentations to learn more about what interesting modern experiments can be done with FELs. But before getting to that point, I have to torture you a little bit more with theory. And I want to recap a few slides that we have gone through when it came to understanding undulator radiation at synchrotrons. But I mean, free electron lasers are based on undulators and on undulator radiation uh, very much in the same way as synchrotrons, on with one specific twist that we will make it actually laser-like in the end. We will get to that in a minute. But yeah, just a brief recap um, how we derived the wavelength of the radiation emitted by an undulator. The starting point was electrons, relativistic electrons, flying through an undulator, this periodically poled magnetic field. And then we considered that electrons experience a Lorentz force based on their velocity and the strength of the magnetic field. The force that is equal to the derivative of the momentum, and momentum for relativistic electrons are given by this formula. So by assuming a periodic magnetic field acting in along the y direction and only taking, of course, magnetic field is not a perfect sine or cosine function, but for an undulator where the amplitude of undulation is rather small, this is quite a good approximation that the magnetic field can be taken as a cosine. And then, yeah, going through the math, namely taking the acceleration, so force equals mass times acceleration. And the force is given by the Lorentz force, where we stick in the expression for the magnetic field in the B here. Then we arrived at an expression for the velocity in x direction, which is like the transverse oscillation transverse to the propagation of the electron along the beamline or along the undulator, which is where this k parameter, this undulator parameter, appeared as a coefficient in front of a sine term, sine of 2 pi z, so the electrons fly along z, divided by the undulator period. The undulator period is just one period of this elementary unit of the undulator. Then we also looked at the total, like the relativistic velocity, v square can be written as vx square plus vz square, and over c, then this is just another way of writing the Lorentz parameter, this gamma parameter here. And then, yeah, without repeating everything, in the end, we got an expression for the average velocity along z, so along the propagation direction of the electrons. So remember, we have a blue equation. The blue is velocity along x. The green equation is the mean velocity along the electron beam. And then finally, by transforming back, so we by transforming back from the rest frame of the electrons back into the lab frame, which is done by using the Doppler formula, yeah, because the light emitted by the fast-moving electrons in the rest frame of the electrons, once we transform back into the lab frame, the wavelength gets shifted by the Doppler effect, the relativistic Doppler effect, by this formula here. And in the end, we arrived by this important, we arrived to this important undulator equation, where the leading term is the undulator wavelength divided by 2 times the Lorentz factor square. And then there is a correction, like an additional correction factor, k square, and this is where the magnetic field comes into the play. So basically by tuning the magnetic field, mostly by opening and closing the gap between the permanent magnets in the undulator, we can control this k parameter, and in this way also tune the wavelength, which otherwise is given by the energy entering in the Lorentz factor here in the leading term. And then there's an additional term that comes from the Doppler formula here, which indicates a wavelength dependence as a function of the angle of axis. Okay, so that's a repeat. Now we start with something new. And what we do now is that we consider an additional external electromagnetic field. So we have the undulator motion, the undulation of the electron as it passes through the magnetic field, and we add an extra external light field. And now the question is, can this light field interact somehow with the electrons and exchange energy? Can the light field accelerate or decelerate the electrons? Yeah, can there be any kind of of energy exchange between the light field and the electrons. So the way of answering this question is to calculate the average power from the interaction of the light field with the electrons, and the power, like whether the electrons absorb power from the light field or they emit power into the light field. This is given by, power is something like energy divided by time, and energy is force times displacement, so F times x. So divided by time gives us a force, so E elementary charge times the electric field times the velocity. Question is, if we average this scalar product over time, does this vanish, or does it give some finite number, which would mean that the electrons actually absorb or emit energy from the light field? So to calculate that, we assume, and we know that the electrons move both transverse direction to their propagation. So that's the x dot, and they have a mean velocity along x. So that's the velocity vector of the electrons. The electric field travels in the same direction as the electrons. So but the polarization, the electric field, points in the transverse to their propagation direction. So we choose to have the electric field point in the x direction times some cosine kz, where k is now the wave number of the light field minus frequency of the light field times t, and there can be some phase, some arbitrary phase of this electric field with respect to the undulation motion of the electrons. So that's our starting point. Now let's take the scalar product to calculate the power, and that is since we chose the field to point in x, and the velocity has x and z. Scalar product is just a scalar number now. So it's the expression. Now we have to remember the blue equation. The blue was the velocity in x. So we stick in the blue equation times the cosine function for the force. And so we have a product of a sine function, ku times z. Ku is 2 pi over lambda u. So that's the wave number of the electron oscillation or undulation, times, here we have a kl times z minus omega t. And a product between a sine and a cosine, there you have to remember trigonometric identities. So sine A times cosine B can be written as sine A plus B plus sine A minus B divided by 2. So we get two contributions, two terms, one with one with the sum of Ku plus KL, and one with a difference Ku minus KL. And also the there's a minus omega LT and a plus omega LT. So essentially two sine functions with two different phases. And for that, in the end, we have to calculate the time averaged value to see if, like, on average, there is any positive interaction, in the sense that the light couples to the electron, accelerates the electrons over the whole interaction time, or possibly the reverse happens, and the electron gets slowed down and emits power into the light wave. So the question is, time average, does it average out to 0 or not? And There we have to consider two cases. So if both these phases, the phase phi and phase chi, if both would be unequal 0, this would mean that we would have a sign of a time varying function, or sorry, we would have like a sinusoidal sinusoidally varying function as a function of time, both for this term and for this term. And now if we average over time over these sine functions that vary with time, those would average out, right? Because just the average taken over a long period of time over oscillating sine functions just average out to 0. So the condition actually that the time average is non-zero would be that either the phase phi or the phase chi are 0. Because if, let's say, phase phi is 0, then we are left with sine of some constant phase, which could be 0. Okay, if it's 0, then the whole sign would be 0. But if phi naught is non-zero and phi of t is 0, then we are left with sine of a constant, which is a constant, and we would actually have a constant finite value for the time average. So one of the two phases have to be 0. And in that case, we get a constant contribution, which in the time averaging then would give us a finite contribution. So this is also called the secular term, in contrast to the oscillating terms, which would average to 0. Of course, also both of them could be 0. That would also work. But if you go through the math, we find out that both, because one is plus, one is minus, both cannot be 0 at the same time. Only one of the two can be 0. So let's pick phi of t and see, and like set phi of t equals 0. So we are setting this phase here to 0. Now we remember the green equation. The green equation was the one for the average z velocity, which we stick in here. Yeah, so I mean, here the z, we can replace z by average z times t. Then pull out the t when we equal this to 0. So either t is 0, but I mean t should not always be 0. T should advance in time. So so the parentheses have to be 0. So if the parenthesis is 0, then we finally get to this equation, remembering that the ku is just 2 pi over lambda u. So we can isolate, like replace here lambda, and also KL is 2 pi over lambda L. So what we find is that the wavelength of the light, in order for the light to actually couple to the undulating electron beam and either absorb energy or like transfer energy, this only works if the wavelength of the light exactly matches the undulator equation. So exactly matches the wavelength of the undulator radiation that is emitted by the electrons. And this condition, that the external electric field has to have the same wavelength as the undulator radiation, this is called the undulator resonance condition. Only if that condition is fulfilled, then we can couple to the undulator radiation. Yeah, that's the undulator resonance condition. And then the question is, I mean, do the electrons absorb light, absorb energy from the light field, or do the electrons get slowed down by interaction with the light field and add energy by emitting light into the light wave? And that obviously depends on the phase, phi naught. So this can be visualized in these three diagrams. So in the case that phi naught is 0, and what is shown here as the blue arrow is the velocity of the electrons, yeah, as the electron undulate through the magnetic field. Here at the 0 crossing, the electron velocity just points upwards. If phi 0 is 0, it means that there is a velocity pointing upwards, but no electric field at that point, at that position here. So no interaction, no power absorbed or emitted. But if the phase is pi over 2, then the electric field of the external wave points in the same direction as the velocity of the electrons. And then we get negative absorbed power, because a negative because the electron has this minus sign. Yeah, so there's a minus here, which means that there now is a net transfer of energy from the electrons to the light, meaning that the electrons get decelerated, and like when the electron get decelerated, where does the electron energy go? Well, it goes into amplification of the light field. Or for the phi naught phase of being minus pi over 2, there the electric field of the external wave points opposite to the velocity of the electrons. And in this case, we get, due to the minus sign, we get acceleration of the electrons. So the electrons absorb energy from the light field, and the light wave obviously gets then attenuated. So yeah, basically we have a coupling between a phase shift of the external electric field and the energy change. The point is that when electrons get decelerated at phi equals pi half, they would eventually slow down and shift in phase. And if the opposite case happens, that the electrons are accelerated, they would speed up, and eventually the phase would advance, right? So there is a coupling between the phase shift, the relative phase between the light field and the electron motion, and an energy change, absorption or emission of energy from the light field. And also the back process happens, a phase shift induces change of energy. So this gives us a feedback loop. And a feedback loop can be formulated in terms of a pendulum equation. So we can actually, by linearization, by some derivations, you can see, for example, here this lecture script where all the math is worked out. We can derive a set of coupled differential equations. These are just first order differential equations that couple the phase phi and the Lorentz parameter gamma, which is proportional to the energy of the electrons. Yeah, so there's two this set of differential equations. Should be noted that we have a sine phi here, so this is a nonlinear pendulum equation, where the amplitude A here is given by this parameter. Yeah, so now let's consider a first case. As a first case, we have, let's consider this one where transfer of energy goes from the light to the electron beam, and the electrons get accelerated, which goes at the expense of light attenuation. So this actually has been realized in an experiment already quite a while ago. Yeah, 25 years ago, there had been a first experiment at a synchrotron. So this is not a free electron laser. It is coupling of a light field with the electron bunches as they travel through the undulator, but no FEL activity yet. This type of interaction is called femtosecond slicing of synchrotron of electron bunches, and therefore synchrotron radiation. And the way it works is that this intense femtosecond laser pulse is superimposed onto the electron bunch as it travels through the undulator. And I mean, remember that an electron bunch is quite a long sausage. This is just in time 30 picoseconds or sometimes 100 picoseconds even long. So much longer than the femtosecond pulse. Femtosecond, this was probably around 30 femtoseconds, so a factor 1000 shorter and quite intense. So now, in order to meet this resonance condition, right? Remember, this all only works if the undulator resonance condition is fulfilled. So if the laser wavelength just matches the wavelength of the undulator radiation emitted by the electrons. So in that case, we can have coupling of the laser pulses to the electron motion. And yeah, a small fraction, so just this slice of electrons in the bunch, for example, gets accelerated. And if the phase is chosen properly, that slice of electrons would be accelerated forward, which does not yet mean that this slice of electrons actually moves away out of the electrons in that part of the bunch. Because I mean, remember, these electrons are highly relativistic. They all travel at nearly the speed of light. So by adding a little bit of energy, does not mean that the electrons actually start moving differently. They're just more energetic, but they all still continue moving at the speed of light, more or less. So the only way to then really make them spatially displaced due to this energy kick that they got is by sending this energy modulated electron bunch now through a dispersive element. And by dispersive element, I mean this has to be an element that converts energy into spatial displacement, just like a prism converts energy of light. So the color of light into this different diffraction into different directions behind the prism. In the same way, there are dispersive elements for electrons, and these are, in the simplest case, just bending magnets. Because in the bending magnet, the electron trajectories, as they are bent around the magnetic field, would have different bending radii depending on the electron energy. So in this way, now really the energy modulation is transformed into spatial modulation. And yeah, so the bending magnet here acts as a prism and spatially separates this slice of accelerated electrons away from the main beam. And now in the next bending magnet, remember that any bending magnet that exerts a force and thus an acceleration on electrons also induces the emission of radiation, because any accelerated charge emits radiation. So in this case, this middle bending magnet is the actual source of radiation. And here in the second bending magnet, now we have the two separated electron components, right? The main bunch that continues with its original energy is bent and emits its bending magnet spectrum. And then there is the spatially separated, very short, like femtosecond slice, which is separated out of the beam, which also emits synchrotron radiation or bending magnet radiation, but only in this very short slice of electrons, which is like spatially separated. So we get a spatially separated, very short pulse of radiation, which then using a set of slits can be separated out of the main beam of light that is emitted from the main bunch that continues traveling along the beam line or along the accelerator here, whereas the X-ray light is like scraped. The femtosecond X-ray pulse is scraped out of the main synchrotron pulse and can be focused, and yeah, so it can. That's represented here. We have like the main picosecond pulse then has a hole where the femtosecond laser has had carved out this slice by energy modulation and slightly displaced from the main beam, we get this femtosecond pulse. So this is actually a way to produce femtosecond X-ray pulses. It's called femtosecond slicing and had been implemented in various synchrotron facilities, also at Electra Synchrotron, where Shivarama Krishnan and I have been doing a lot of experiments. But it is not really very fashionable anymore to produce femtosecond X-ray pulses in this way, because it mainly has become obsolete since we have free electron lasers now, which also produce femtosecond laser pulses or X-ray pulses at much higher intensities and with many more degrees of freedom to control intensity, pulse duration, and so on. So there is still a few facilities where people continue working on femtosecond slicing, in particular Bessie synchrotron in Berlin, but mainly this has been replaced by free electron lasers now. So, I mean, the advantage of this technique is that this offers a way of producing tunable femtosecond X-ray pulses. Yeah, tunable, just like synchrotron radiation is photon energy tunable. And it is naturally synchronized with the laser pulse. So this offers, in principle, good possibilities to do pump probe, where then, for example, this optical laser pulse would be used for preparing some initial state by shining this pulse onto a molecule or some sample to excite it, and then using the ultra-short X-ray pulse, we could probe the dynamics of what's happening right after the excitation, for example. But yeah, the disadvantage is that the photon number obviously is very low, because even a single pulse emitted from a single electron bunch at a bending magnet already produces very low total number of photons, like total power or energy in such a synchrotron pulse is very low. And then if we like manage to cut out this tiny slice, then the photon number is extremely low. So essentially the only type of experiments that can be done are some solid state experiments where we have a very high target density, where even a few photons would make a difference. Yeah, another disadvantage is that this bunch modulation, if this is done in a storage ring and this electron bunch is supposed to produce synchrotron radiation in other sections of the storage ring, then we would have this modulation here on all the beam lines along the storage ring, along the synchrotron. So other users would probably complain about this strange time structure of their pulses. And yeah, this is still just bending magnet radiation. So this is not really coherent radiation. Yeah, here's just a brief estimate of the ratio of like photon number that we might expect. I mean, we have femtosecond, or like the number of photons in the femtosecond laser pulse divided by the number of photons in the total picosecond bunch or pulse from the whole electron bunch is given just by the ratio of the pulse durations. And yeah, so this is like, let's say 100 femtoseconds, which is 0.1 pico divided by 30 pico in the, yeah, around a thousandth or so of number of photons in this femtosecond pulse, which is very low. Okay, so that was the case. So nothing about free electron lasers. This was the case of coupling energy from an external laser field into the electron bunch. But now let's consider the other case, the case that there is now energy transfer from the electrons into the light field, which would decelerate the electron beam, but it would amplify the light field. So yeah, this amplification, this already sounds like laser activity. I mean, laser is also relies on light amplification by stimulated emission of radiation, right? That's what laser means. And how does this work? Well, their nature is actually kind to us and provides us with a self-amplifying mechanism. So consider a bunch of electrons. So this is actually a very long bunch. So these are all electrons extended over a length of 2 meters inside the undulator. And now what happens is when these electrons are dense enough that they emit a lot of undulator radiation. So they themselves create an external electric field. Yeah, now there's no laser pulse that we shine in from the outside, but the electrons themselves emit undulator radiation, right? And this undulator radiation, if it's intense enough, so if there's enough electrons that emit light, then eventually all this undulator radiation would couple back to the electrons and produce some energy modulation, just like the femtosecond pulse induced an energy modulation. So after a few more meters of propagation, then we would see that electrons, due to this energy modulation, start rearranging into what is called microbunches. So within the whole like 30 picosecond electron bunch, the electrons would be pushed slightly into these into like small regions of higher density and lower density. And as the electron bunches propagate and continue emitting undulator radiation, this bunching continues and actually becomes stronger and stronger, because what helps us is that as the electrons arrange themselves in this regular pattern, the undulator radiation, the total intensity of undulator radiation like shoots up because the undulator radiation is emitted now in phase. Yeah, these electrons arrange themselves along the like in periods of the wavelength, and the wavelength naturally matches the undulator resonance condition, so that we have naturally occurring resonance condition of the radiation, and then back coupling to the electron bunch. And yeah, so this is a positive feedback loop. And this process of microbunching and amplifying the radiation is also called the free electron laser instability. It's like a an instability of the phase space distribution that spontaneously occurs due to the positive feedback coupling of the undulator radiation emitted by the electron themselves and then coupling back to the electron distribution. So initially, this microbunching process works in this way. Initially, phases of the emitted light, these phases phi, are random because it starts out of shot noise. These electrons are completely randomly distributed. So this is very similar to laser activity. Remember, a laser starts lasing out of the spontaneous emitted photons. When you switch on the laser, first there is no laser light. There is only some excited laser medium, which emits spontaneous photons. And once the first spontaneous photons comes, that just meets the resonance condition of the optical resonator and would be reflected back and forth through the gain medium, then this spontaneous photon would trigger a first stimulated emission, which produces a second photon. Then these two in-phase photons would trigger another stimulated emission process, and so on. So we get an avalanche-like increase of emission of light, and that is exactly the same mechanism happening here. Yeah, so I mean, initially these phases are random. There's no net exchange, but if the undulator radiation is intense enough, then electrons that happen to be near this plus or minus pi over 2, they would couple to the electron bunches most strongly, right? Because there this time average over force times velocity is largest, either positive or negative, which produces an energy modulation. Yeah, some slices of electrons are pushed forward, some slices of electrons are pushed backwards. The energy modulation then, as the bunch propagates over sufficiently long distance, this energy modulation converts into density modulation, via phase slippage. But this takes quite some time. So clearly these undulators where microbunching is supposed to happen have to be quite long. You can see many meters of length where this happens to allow for the coupling to evolve, and then also to allow for this conversion of energy modulation into density modulation in real space. And yeah, eventually the electrons would would cluster near stable points of this pendulum that's given by the pendulum equations. And these fixed points actually just correspond to to a phase of plus pi over 2, which is just the condition for electron deceleration and light amplification. So that's the stable points in the pendulum system, which mean maximum light amplification and maximum conversion of electron kinetic energy into light. Of course, this cannot go on for eternally, because eventually the electrons would lose their kinetic energy and then run out of this phase condition again, and then light amplification would saturate. Yeah, so but this process of spontaneous coupling of the electron bunches to their own radiation field, this is called the free electron laser instability. And yeah, in terms of gain or pulse energy of the emitted laser or light pulses, as the microbunching evolves from a completely random distributed electron bunch into a fully micro-bunched structure here. This easily can lead to a gain, so an amplification of the radiation field by 4 to 5 orders of magnitude. Yeah, so here it goes from 10 to the minus 8 up to 10 to the minus 4 joule. So from nanojoule to 100 microjoule or so of energy per pulse within the length of, how much is it? 5 to 6 meters. And then eventually saturation happens and all the energy of the electrons is converted into the light, and that's the max we can get. Yeah, so by definition, we can formulate definition that this process of spontaneous self-amplification of uh, uh, so SASs, self-amplification of spontaneous emission. It starts from spontaneous emission, which is then amplified in this self-consistent way, is defined as a runaway instability in which the microscopic shot noise from the initially randomly distributed electrons is exponentially amplified by a self-consistent electron radiation interaction. Yeah, and the fact that the electrons, like initially, emit light in this completely uncorrelated, like phase uncorrelated fashion means that the intensity scales as just proportional to the number of electrons, because like every electron emits by itself, and the intensities add up. Intensities emitted by every electron add up incoherently, but once microbunching has occurred and all electrons now are arranged in the like nodes or antinodes of the light field, then the light emission is in phase, and we get coherent emission of light. So this is very similar to laser radiation, and the intensity now scales as the square of the number of emitting electrons. So yeah, so that's the SASA process, and like the initial realization obviously was done in an arrangement very similar to a conventional laser, only that the gain medium is now replaced by undulator structure. But why not build a laser resonator around it? So maybe some of you would now shout out and say, "But wait a minute! I mean, we always kept saying that it's not possible to build a resonator. Like there's no mirrors for the X-ray." That's absolutely true for X-rays, but I mean, in the undulator, we have free transitions. So in principle, we can tune an undulator to any wavelength that we want. It doesn't have to be X-rays, right? We can also tune it to visible or to the infrared. And then we do have mirrors, and we can easily build a resonator around it. Yeah, undulators can emit light at any wavelength in principle. So in particular, also in the far infrared or the terahertz region. And this is particularly interesting region of the electromagnetic spectrum because here we don't have other radiation sources like standard lasers. There is due to like absorption of this radiation by any material, including air. It's very hard to build a conventional laser in the far infrared or terahertz region. So free electron lasers are actually a nice way of creating intense radiation in this range. And in this range, it's very easy to build a resonator because there's like almost any metal surface has a high reflectivity. So we can just use metal mirrors. And And then, yeah, thanks to this resonator, where the radiation is like resonantly enhanced by being reflected many, many times back and forth and actually forming standing waves inside the resonator, then this, of course, facilitates the coupling to the electron bunches and enhances this Sarse process. And that's a way to build a laser based on undulator radiation. And these facilities actually exist. So for example, here, what is shown on the left is the so-called Felix and Felice. So Felix is terahertz free electron laser going from 30 micrometer. So this is micrometer radiation. Yeah, this is far infrared. Sorry, this is terahertz, 150 micrometer, and Felice is far infrared, 5 to 100 micrometer. Just two different setups of free electron lasers based on undulators and optical cavities built around them. And actually, they are even built such that the undulator is, I think, down in the basement, and then the resonator is folded like this, such that the actual experiment is taking place on the first floor, because the light is sent upwards onto the first floor, where the back reflecting mirror is. So actually, in these setups, the experiments are done intra cavity. The light is not outcoupled, but it's just used to create very resonance enhanced fields inside the laser resonator to do some molecular spectroscopy, for example, in the far infrared. Another facility is at the Fritz Haber Institute, that's in Berlin. So by the way, Felix and Felice are user facilities in Nijmegen in Netherlands. So you can actually apply for beam time if you have a good idea how to use intense far infrared radiation for molecular spectroscopy mostly. You can apply for beam time here. The free electron laser at the Fritz Haber Institute is an in-house facility, but very similar. Okay, so this is the free electron laser built in a very similar way as a normal laser, only that the gain medium is replaced by an undulator. And yeah, the quantum transitions between laser levels that are which are transitions between quantized levels in some gain medium here are replaced by free transitions of the free electrons undulating in the undulator magnetic field. But the physics is very much the same. Yeah, so advantages of this type of free electron lasers is that power can be very high, in particular since the power now scales as the square of the number of electrons due to the coherent emission of radiation. Compared to like regular synchrotron undulator radiation, the beam here is better controlled and like has a smaller divergence and also smaller beam radius given by the resonator, and like the quality of the resonator, which can be very high. So we can control the beam parameters better than just let's say the spontaneously emitted undulator radiation. Also, the spectrum becomes much narrower. Remember the discussion we had for the laser line width that can be extremely narrow, just given by the condition of gain equals losses that can define a very tiny point in the frequency spectrum. And yeah, we can have full transverse coherence because this is like really laser-like light emission. Yeah, so that's all nice, but it again works only in spectral regions where we have resonator mirrors to build an optical cavity. And this does not work for in the X-ray. So how can we beat this? How can we cope with this issue? And yeah, that essentially we already talked about this. This is the SASA principle, and yeah, this so this spontaneous self-amplification by of spontaneous emission uh, is very similar to what we had talked about in the very first lecture, like amplified spontaneous emission that even happens in natural systems, like in molecular clouds or like in atmospheres of planets, where molecules can be in excited mainly hyperfine and spin states and like molecular, very long-lived molecular states. There, of course, there is no resonators, but these excited molecules, they exist in huge amounts, covering very large areas. And there, what can happen is that a first spontaneously emitted seed photon, just due to the sheer length of the gain medium, has a chance to hit another excited atom or molecule, produce a stimulated photon, which then again amplify the light in this avalanche-like way, but with no optical feedback, just in a single pass. And that is called amplified spontaneous emission or super radiance. And that can actually happen also in an undulator, provided the undulator is long enough that we give the undulator radiation that is initially emitted completely spontaneously here. We give it enough interaction length and like enough chance to then interact with the electron bunch, induce the microbunching, and then as the microbunching sets in, the electrons start emitting in phase in this coherent fashion. And here what is shown on the bottom is the radiated power, but the logarithm of it. So a linear increase actually means an exponential increase of radiated power along this long undulator until saturation sets in, and then the electrons would also move out of phase again, and the gain stops. But yeah, and so that's the actual SASE principle, and there is advantages to it, of course, namely that it doesn't need any resonators, so there's no limitations to the wavelength. In principle, if the electron energy is high enough, then we can produce very highly energetic hard X-rays in this way. We can generate very high output power. Since this emission is coherent, we get the low beam divergence, but still, I mean, the quality is not as good as if we had a resonator. Of course, an optical resonator helps to get very clean both spatial and spectral properties of the radiation. This is still radiation born out of spontaneous emission. But yeah, it's a low divergence beam. But in order to realize this SASE mechanism, it imposes extreme demands on the electron beam, in the sense that it needs very high beam current. Because imagine that this undulator radiation has to be strong enough to back couple to the electron bunch and to actually like influence the motion of the electrons, which means that the magnetic field of the undulator radiation emitted by the electrons has to be like in the order of magnitude of the external magnetic field from the undulator itself, which is on the order of a Tesla or so. So the undulator radiation has to produce electromagnetic radiation where the magnetic field component has has a strength on the order of a Tesla to compete with just the forces acting on the electrons from the magnetic field of the undulator. And that requires like very intense radiation, and that requires very dense electron beam in the first place. So we need very high beam current. We need a very low emittance, meaning like a small divergence of the electron beam, low energy spread. The electrons have to be all quite monoenergetic in the first place, and we need long undulators to give this process a chance to develop over one single pass of the electron bunch through the undulator. And yeah, so this requires very high imposes high demands on the precision of machining all these devices and controlling the position of the magnets on this very long, like many meters long length scale. Yeah, so I mentioned, so we need the high intensity of the undulator radiation to produce magnetic field. I mean, the magnetic field just from Maxwell's equation scale as electric field divided by C. So this division by C, of course, reduces usually the magnetic field component of electromagnetic radiation to very low values so that in many cases the magnetic field can be neglected and we only consider the electric field. But here the magnetic field has to be on the order of a Tesla to match the undulator magnetic field so that it has any effect on the bunch propagation and the electron propagation inside the undulator, which means on the other side that the intensity has to be like on the order of 10 to the 10 watts per square centimeter, so very intense. Yeah, it requires high electron energy in order to realize this high power of irradiated undulator radiation. I remember the formula for power scales as the electron energy square. So every giga electron volt of extra electron energy will help us to increase the intensity of irradiated power. We need a very small electron beam on the 10 micrometer square length scale or short pulses. So in this case, the electron bunches should be not picosecond or like 30 picosecond long, but they should be femtoseconds long to compress all the electrons into very short bunches, again, to increase the electron density as much as possible. We need long undulators on the length scale of 10 meters and very precise alignment of the setup so precision in the range of 10 micrometer on a length of 10 meters. So this is a factor of 10 to the 6, so 1 million is the precision that's needed. And even then, so the typical conversion efficiency from electron energy into X-ray power is still better than high harmonic generation in laser matter interaction, but we are talking about 5 times 10 to the minus 4 or so. All right. I think this is a good moment to take a short break. And actually, we have another little quiz that is designed for making you recap what we have been talking about yesterday and partly like last week. So after this quiz, we could then talk a little bit more about the technical aspects of realizing free electron lasers. So Tanu,